1.2d, dividing decimals. When dividing with decimals, it is a good idea to shift decimal places in both numbers until both are whole numbers. So what I mean by this is, say we had a number like 1.2 dividing into a number 3.5. Let's see, we had something like that. I would shift both of the numbers a decimal place to the right in order to make them whole numbers. So this 1.2 would become a 12, and the 3.5 would become 35. And then I would carry out division like normal. This is called an equivalent problem, because the solution to this problem is the same as the solution to this problem, with one difference though. We have to shift the remainder back over the opposite way we shifted. So we have to shift the remainder back over. Back over. And you'll see what I mean by this in the first example. So we can solve the problem like a normal long division problem. The strategy is not always used, but for a lot of decimal problems, it turns them into much simpler ones. So let's look at the first example. Compute 25 divided by 1.5. So we write this out in long division fashion. So 1.5 goes on the outside and 25 on the inside, right? And I don't like the fact that 1.5 is a decimal, so I'm going to shift this over by 1. But that means I have to shift the decimal in 25 over by 1. And since there's no decimal, we assume there's one here with that invisible 0, right? 25.0 is the same as 25. So when I shift this over, that means it's going to turn into 250. So now this problem becomes 15 dividing into 250. So we have to look at the first two numbers, since 15 is a two-digit number, and 15 goes into 25 once, and we're left with 10. Drop down the 0. 15 goes into 100 6 times, and 15 times 6 is 90. So 100 minus 90 is, sorry, I should have written 15 here. Minus, that gets you 100, and then 100 minus 90 gives you 10. So we have a remainder 10. But we have to be careful because our remainder is not actually 10. Because look at our original problem, 25 divided by 1.5. If our remainder was 10 and we were dividing by 1.5, that wouldn't make sense because we could divide further into it. So let's go ahead and shift this over by 1 to make it 1.0. So our answer is actually 16 remainder of 1. Now let's try a different type of decimal problem in which our answer is expected to be a decimal because we're dividing by a larger number. So we're going to divide 19.5 by 25. So notice that 25 doesn't go into 19 or 19.5. So we have to pretend here. We have to pretend that 19.5 is actually 195, but it's not. What we would have to do to get our answer to be 195 is shift our decimal place over by 1. And in order to do that, we have to start on the right side of the decimal. So 25 goes into 195 7 times. So 25 times 7 is 175, and the decimal place goes here, and we're left with 2.00. So 25 doesn't go into 2. If we shift it over by 1, 25 doesn't go into 20. So we have to shift it over by 2, and in order to do that, we have to start in the second decimal place, since we've shifted over by 2 to make it something we can divide into. So 25 goes into 200 8 times, and that's our answer, is 0.78 is our final answer. And we expect this to be less than 1 because we're dividing by something larger. So now let's apply this to a real-world problem. So say my shop has $1,200 to spend on bolts this year. If the manufacturer quotes us at 50 cents per bolt, how many bolts can we buy? So we divide the amount of money by the cost per bolt. So 1,200 goes on the inside and 0.5 goes on the outside. So now we can look at this instead of as a problem with decimals as a problem with whole numbers. So this now becomes, with shifting over the decimal point by 1, it becomes 5 dividing into 120,000. So 5 goes into 12 how many times? 5 goes into 12 twice. We subtract a 10 from there, and we're left with a 2. Bring down the 0. 5 goes into 24 times, and we have 2 leftover zeros that come on up. So our answer is 2,400 bolts is the amount that we can purchase.